Hello, everyone. Can you hear me?
I can hear you just fine. Good morning.
Yeah, good morning, everyone. Yeah, hope you have a nice weekend. Okay. Okay, so yeah, this is a new week, and let's try to continue our last week's lecture. Okay. So let me share my screen. Okay, let me know if my sharing looks good or not. Looks good or not?
Looks fine.
Looks good.
Okay. Okay, that's good. Okay, so I think last week we talked about different switching methods, right? So we have a packet switching, we have circuit switching. So for circuit switching, I think some of you may still remember that it is a very commonly used method in communication, right? So you can establish the communication with other people you want to call, you want to talk, right? Talk to, and but after you establish the connection, that link is dedicated to you, right? So there is some good thing or not good thing, right? Or bad thing. Good thing that you can almost dominate the full bandwidth or capacity of that link, right? But the bad thing that you cannot share the link with other people's. So we have the frequency division multiplexing and the time division multiplexing. Still remember? So for the frequency division multiplexing, everyone, the signal is go through in the link, but they are based on the different frequency, right? So they can, in this case, for example, we have the 4 users, we have 4 different frequencies. They can share the 1/4 of the full bandwidth. But for the time division multiplexing, based on the time, right? So they can share the different time slots. So each user can dominate the full bandwidth or capacity of the link, right? But for the 2 different methods, there are many used for or in the different cases. For example, the FDM frequency division multiplexing, they are mostly used for analog signals, right? Because they're based on the frequency. They have to decompose the frequency into the different band, different data, right? For the time division multiplexing, so mostly they're used for digital data. Okay, so as I mentioned, there is some other approach for the circuit switching, like a statistical time division multiplexing, STDM. Okay, so the idea is just straightforward because not every user has to use the same amount of the time, right? They can use a different amount of time. You can, based on the statistical information, to divide the time interval based on the demand, right? So this is just straightforward here. And so if we compare the circuit switching with the packet switching, okay, there is some thing interesting here if we compare the 2 different methods. So generally speaking, the packet switching allows more users to use the network. So why we can say this? We can say this. So for example, if we consider a link, okay, with 1 gigabits per second, the bandwidth, okay, so each user needs to use a 100 megabits per second when active, but they only active in 10% of the time. Okay, let's do this assumption. Okay, so based on the circuit switching, so we can say that at most we have 10 users to be active at the same time, right? Because each user needs 100 megabits per second when they are active. Okay, so 10 gigabits divided by 100 megabits. So you can have only about 10 users at the same time. But what about the packet switching? So for packet switching, we can say that we can have about 35 users to be active at the same time. And the probability to be larger than 10 active users is only about 0.04%. Okay, so how can we get this value? So I mean, if you learn the probability, you know that if the probability is around 0.04%, it's very low probability. That means mostly the 35 users, when they use the network, the probability larger than the 10 active user is almost impossible, because this is a very, very low probability. But the question is that how can we get this probability, right? Okay, this is our question. But before we answer this question, the conclusion is that if you have 35 users, these users are trying to use the network, right? And different or unlike circuit switching, they can only allow 10 users. But now we have 35 users, and the probability for more than 10 active users is only about a very, very low probability. So that means we can say that the 35 users can use the network and do not incur any severe problem. So that's our conclusion, right? But how can we get this probability? This is our problem want to solve. And another question is that, okay, if I have more than 35 users, right? I have 40 users, I have 100 users, what will happen? So I think this question is simple, because if you have more users, the probability larger than 10 active users would increase, right? But how we can do the calculation to calculate the probability, that's our question, okay? So let's review probability basic Bologna trials. Maybe some of you know that. If you don't know that, that's fine, okay? This is something we give you as an extra information, how we can calculate the probability, okay? So let's assume the P to be the probability of some event A, right? So for example, if we toss a coin, right? So A is the event that the outcome is tails, right? Another is the event is that the head of the coin, right? So you have the two events. I mean, the outcome of the event has two cases, right? And assume that you conduct n independent experiments, right? So examples of this are when you toss the coin n times in succession, and when you throw a dice n times in succession. So we can calculate the probability that the event A will occur X times. So I think the probability that X out of n tosses result in a tail or head is based on this formula. So I mean, if you learn the probability class, this is, I think, is the basic, right? Because you can calculate the successive events, the probability of the event happening at the same time, right? And usually we know this as a binomial distribution, okay? So we use a toss a coin as an example. And but if we revisit our problem, okay, in our case, A is the event that a user is transmitting or using the network, okay? Therefore, that P is equal to 0.1 and X is equal to 10. So why P is equal to 0.1? Anyone knows that why P is equal to 0.1?
Because users are active 10% of the time.
Okay, yes, correct. Yes, because users are using only 10% of the time. So the probability of the event A is only 0.1, right? 10%. So and X is equal to 10. So we want to the event to happening, right, at least 10 times. So the probability that X is larger than 10 is equal to 1 minus px not larger than 10, right? Or smaller or equal to 10, okay? And then we use the 1 minus px equal to 0, x equal to 1, 2, until 10, right? To calculate each probability, okay? And in this case, n is equal to 35 because we have 35 users, okay? And x can be happen once or twice or 3 times until 10 times, right? We use a 1 minus those numbers. And finally, we get that the probability of x larger than 10 is equal to 0.04 percentage, okay, or 0.0004. Okay, so this means that more than 10 users out of 35 users transmitting the data or sending or using the network is equal to 0.04 percentage. So that means we calculate a very low probability that more than 10 users would use the network. Okay, let's go back to this slide. So what does this tell us? As I mentioned, this tells us that you can have more users you can allow more users to use the network simultaneously, but you can expect that more than 10 active users to use the network is a very low probability, right? In a very low probability. Okay, so in a high level conclusion, this tell us that packet switching allows more users to use the network. But the circuit switching, because you dominate the network, right? You can link so that it will limit your, I mean, the upper bound of the users can be shared, can share the network, right? So this is some advantage of a packet switching. Okay, but I don't expect you to do a calculation because some students may ask, do we need to calculate this probability? I don't expect you calculate this complete probability, because you can see that here you need to calculate a lot of binomial probability here or distribution here, right? But from high level, you need to understand why packet switching has a more flexibility or can tolerate more users than the circuit switching. Okay. Let me check if there is any problem in the chat. Maybe there's a message there. Issue if more than 10 actual users, even if a chance is small. Good question. I wonder if maybe some kind of packet connection loss occurs. Okay, here I think the assumption is that there is no loss or something happen here. Okay, we based on a perfect assumption. Okay, just about a very straightforward and simple assumption. Okay, we will talk about packet loss or something. Why bad thing happen? Definitely, you need to re-grab the data, right? But here we just based on a perfect assumption. Okay, so and then yeah, this is a good question. Then we talk about packet switching versus the circuit switching, right? You definitely have some disadvantage of packet switching, right? Nothing is perfect, right? You get something, but definitely you will lose something. So for the packet switching versus the circuit switching, it's great for bursty data, right? Sometimes the data has to be sent, but not always the resource. And I mean, you need to dominate the full bandwidth, right? So you can share the resources. It's a simpler, no call for the setup, right? It's not like a telecommunication. You have to first establish the connection with someone, and then you dominate the link and you just call the other people, right? You don't need to do the call setup. But as I think Bryce mentioned in the chat that there will be some problem. For example, the congestion, right? It is possible that the packet will be delayed, will be lost due to buffer overflow. So we will give you an example in the following several slides to talk about how the packet delay and loss would happen. And in the future chapter, we will talk about the different protocols to protect if a packet is lost, and how, for example, TCP will protect the lost packet, right? Definitely, you need to guarantee every packet will be sent, okay? And how to provide a circuit-like behavior. So the bandwidth guarantee is traditionally used for audio and video applications. Okay, so we will, the packet switching can also try to guarantee the bandwidth, right, for the audio video applications. Okay, so here is some comparison. Let's see if I have any question. I'm gonna guess that maybe the speed of the course to divide almost everyone. Yes. Okay, so this is a comparison. For more detail about the packet switching loss delay, we will cover in the later slides. But here, just from high-level comparison, you need to understand the difference between circuit switching and the packet switching. What is the benefit from packet switching? What is the benefit from circuit switching? Okay. Yes, this is the last question, but I think we have explained that. And next topic is about the internet structure. So I think I have mentioned that the internet structure, we usually call it a network of networks, right? So for the internet structure, it consists of multiple or different networks, right? And but for the details about the structure or networks, so we will talk about here. Okay, so first we have already talked about the host connection to the network through the access internet service provider, right? ISPs. I think we mentioned that before, right? You can connect the residential enterprise the network to these ISPs, right? You can also connect to the global ISPs, okay? And the access to ISP in turns must be interconnected. So you have to make sure that all the ISPs to be connected together, okay? Otherwise, the packet will not find the final destination, right? To different, using different IPs. And the resulting network of networks would be a very complicated and complex. And this evolution was driven by the economics and the different national policies, right? Different regions and different areas. So we have to do a step-by-step approach to describe the current internet structure. Okay, so in the following several slides, we will discuss how the current internet looks like based on the concept of network of networks. Okay, so let's see. So here, if we have multiple or many access internet, we have to connect to the internet. So if we connect each other using direct link, right? So how many links we need to have, right? For example, if we have n points, right, or access point. So if we want to connect them to each other, we must have n square, right? N square links to connect to each other. If we use a direct approach, okay. So if we considering there are millions of the access ISPs, so this number will not be possible, right? Because this is a too large number, okay? And I think sometimes it's even impossible you connect two points together because they are in a long distance, right? We have to use some other approach to connect a different access point. Okay, so connecting each access ISP to each other directly doesn't scale, right? Usually it's all n square connections. So what should we do? So an option is that we can connect each access ISP to one global transit ISP. Okay, the customer and provider ISP have an economic agreement. So we have some global ISP here, right? And each access net can be connected to the global ISP, right? That means we have some centralized point, and those points can use as a intermediate point to connect the different access nets, right? And this is only about global ISP, right? You still remember we have the regional ISP, we have the different levels of ISP, right? So for example, there are multiple global ISP, internet service provider, right? So because they are competitors, they want to do their own business. So you can see that we have in this example, we have the 3 ISPs, right? And each access net connect to different ISPs. But the problem is that if we don't connect those global ISPs together, then for example, the access net connect to the ISPA, they cannot connect to the access nets connected to ISPB, right? So that means the different global ISPs need to be connected to each other as well, right? So who will play this role? So usually we will have the internet exchange point to connect the different global ISPs, okay? And sometimes the different ISP will connect to each other directly. They don't use the internet exchange point. But for example, if you see here, let me change to laser. Okay, so if you see here, this internet exchange point, the ISPA, ISPB, and ISPC, the 3 global ISPs can connect to this internet exchange point at the same time, and they can switch or exchange the message or data here, right? But sometimes if ISPB and the ISPC has an agreement, they can also do a peering link to, directly, right? Instead of use a internet exchange point, okay? And some of you may ask a question, oh, where is the internet exchange point? So there are many internet exchange points spreading in the world. For example, this is a figure showing that the internet IXP internet exchange points in Europe, okay? So there are some famous IXP in London, and in some other European countries, okay? So this is about the first level ISP, global ISP connect to the access net, okay? But the problem is that we don't only have the global ISP, right? We have the regional ISP. We also have the content provider. Still remember Google, Facebook, right? They are content providers. They also have the network, right? So here we also have some regional or local ISP. They will connect the global ISP and provide the service to the end user. Okay, so they are between the first level global ISP and the user here. Okay, they are the regional ISP. And also, as I mentioned, we have some content provider network, such as Google, Microsoft, Facebook. They have some data centers. They have some network as well. So those network can connect to the user and connect to the ISP. So they play a separate role in the internet.
So who in the chain would own the IXPs? Are they more of a public service?
Yeah,
or
I think
does a specialized company run them?
I think they are the public service, but there are also some a company running that based on the policy from the different countries. So, for example, the London IXP, so they're mainly managed by the government, but some contractor of the government would be responsible to maintain and do the service for the ISP. Yeah.
Thanks.
Mm-hmm. Okay. So if you look at the internet structure, this figure, okay, you can see that the first level is a tier 1 ISP, okay, the global ISP. And they connect to the access ISP directly. They can also connect to the IXP, right? Internet exchange point. And they can also connect to the content content provider, right? Like Google, and regional ISP connect to the IXP, connect to ISP, right? So you can see this figure mostly describe what we just discussed, the structure of the network of networks. Okay, so at the center is a small number of the well-connected large networks. So this is a tier 1 commercial ISP like Spirit, ATT, NTT, right? National internet, international coverage. And we also have some content provider, right? Just as I mentioned. Okay. So this figure give you the, I think most of the idea of how the internet is composed of, right? Okay, so here is a picture about the tier 1 ISP network. This is a map of the Spirit. Okay, and we can, I think there is a question in the chat. Does this layering of the network decrease the optimal speed of the and the service? I think, yeah, this is a good question. So I think this is a good question. So for example, if you directly connect the tier 1 ISP to your access ISP point, definitely that would be the optimal bandwidth or throughput, right? But problem is that it would be very expensive, and sometimes you don't need such high speed, right, for some service. So for example, if we have the enterprise network like Washington State University, we may directly connect the point to the tier 1, right? But if you are using your home network, you may don't want to directly connect to tier 1, right? You can connect to your regional company, that would be cheaper, but also can satisfy your service, right? So you don't need to directly connect to the tier 1. Right? So I think this is some trade-off between the performance, the price, and the service quality, right? So it depends, right? But this is a good question. Thanks. Mm-hmm. Did I answer your question? Okay, good. Okay, so here we can see that this is a tier 1 ISP network map, Spirit, right? So we can see Spirit provides a lot of I think it's a POPS, right? Or POP, point of presence, right? So it can provide the service directly to the Spirit customer and users. Okay, it can also provide the links peering to other networks or other tier 1 ISP. So this is a figure to describe the Spirit POP locations. Okay. It can also connect to Europe, connect to Asia, connect to different countries. But this is a tier 1. This is the first, the highest level of the ISPs links. Okay, so I think that's the network core. It's a very important concepts and discussion about packet switching, circuit switching, internet structure. Most of them are based on the concepts. We will discuss more detail later, deeper and deeper, right, about packet switching and protocols, different layers, such things. But first, you need to have a high-level understanding, right? What is internet structure and traditional circuit switching and packet switching, okay? So let's continue to the performance of the packet switching, right? Because we send and receive packet, as we mentioned in the previous slides, we will have some loss. And I think last lecture, one student asked a good question, right? So how we can, how do we know the packet is lost and damaged and something? So we will talk about in the TCP protocol or reliable networking protocol, right? About how we can detect, and if we detect, after we detect, how we can react, right? But generally speaking, the packet switching can introduce some loss and delay, right? So let's look at this figure. Okay, so I think this is a figure we have used in the last lecture, right? We have some different users or end users A and B to send their packet to the router, and the router will queue the packet, and then we'll transmit the packet to the link and to the next router and to the next link and then to the destination, right? So here we have some different things happening, right? So for example, as I mentioned, the packet needs to be queued, wait for transmitted, right? And we have the arrival rate to the link. If the arrival rate to the link exists as the output link capacity, the packet will be lost. So it will introduce the packet loss. Okay, generally speaking. So for example, you can see here the packet being transmitted, and the transmission will introduce some delay. You still remember the transmission delay? So it will, the time will be based on the L, right? The packet bits, number of bits, L divided by R, right? R is the transmission rate or the capacity, right? So R divided by R is the transmission delay, right? Besides the transmission delay, so here we want to talk about, we also have some other delay. For example, here, Q delay, right? And we will cover it in the next slides. But besides the transfer delay, besides the Q delay, we also have some propagation delay, right? The data propagating the link, right? We also need to calculate this time. Okay, but here, this slide tells us that if the packet in the buffer and if there is no free buffer, right? So buffer is memory space, right? Is the data space. If you don't have enough space to store the packet, then the only way is just throw out or drop the packet. Then it will introduce some packet dropped and loss, right? If you don't have free buffers here. Okay, so let's see what is the nodal delay. So what's the overall delay if we transfer or transmit one packet here? So as I mentioned, here are totally 4 different types of delays here, okay? As we previously discussed, there is a transmission delay, right? This is the router to process the transmit the packet, right? And we will have the Q delay, okay? And we will have the propagation delay, and we will have the nodal processing delay. We will look at each delay one by one, okay? So the nodal processing is we check the bit errors, we determine the output link. So still remember, we have the routing algorithm, right? And when you receive the packet, you also check if there is any bit error happen, right? So there is some, we can call it a system processing time, right? So this router will spend some time to process the packet and will determine the output link. So it happens on the router. So you can imagine that if your router is more powerful, this delay would be less, right? If I have a very super powerful router, right, and it's expensive, then it will process. You can think about there is a processor, right, in the router to do some calculation based on the algorithm, routing algorithm to determine the output link. Then if the processor is powerful, the delay here would be less. Okay, so this is the first delay for the nodal processing time, and another is the queue delay. So the queue delay is that the packet is waiting in the queue, right, for the transmission. So I will give you an example example based on the car going to the station. That's the example is more straightforward. But here, let's first define the queue delay, right? The queue delay is that you have a lot of packets being queued in the queue, right? And each packet needs to wait some time until they can be transmitted. So this is a queue delay, right? It depends on the congestion level of the routers. If you have a simple example that the router transmit some packet very slowly, but the packet arrive very in a very fast fashion, right? You have 10 packets arrive every second, but you can only transmit one packet every second. Then the queue would be infinite, right? So this is some a certain delay for the queue, right? This is second delay. What about third delay? The third delay is the transmission delay. I think everyone is familiar with this one, right? Because previously we discussed this one. So if we have the packet with the length of L bits and the link transmission rate is about R bits per second. So the transmission delay is L divided by R, okay? And the last delay is the propagation delay. So you still need to think about, even if this propagation is about the speed of light, right? It's still a high delay in some cases. For example, if you transmit the data from the United States to Japan, right? The physical distance is large, right? Even if you have everything perfect, you have a very low queue delay, low transmission delay, low nodal processing delay. But the problem is that the propagation delay would be large, right? Because it's even if it's based on the light speed, the physical distance is large, so you need to consider this delay. Okay. So as I mentioned, right? So the transmission delay and the propagation delay sometimes are very different based on the transmission, the bandwidth, right? And also the physical distance. But the first two, nodal processing and the queue delay, right? Sometimes if the network is stable, you can consider that as a system overhead, right, or delay time. So let's think about caravan case, right? This is a straightforward case for you to understand how we transmit packets. We can think about this. Okay, we can think about this case based on some numbers. So if we have the cars propagate at the 100 kilometers per hour between the two booths, okay, if we think about when you pass a booth, you have to pay some money, right? Or you have to pay some service fee, right? So every 12 seconds, you process or serve one car, right? And this is like a bit transmission time. And we have a 100 kilometers between the two booths, and the car speed, driving speed is about 100 kilometers per hour. So how long until the caravan is lined up before the second two booths? Okay. So how should we calculate the time? So if we have the 10 cars and each cars will be processed, you can think about a car like a bit, right? Each bit we process, or each car we process using the 12 seconds. So how many seconds we need for the 10 cars? It's a 120 seconds, right? So because they have to be processed in a sequential, so 120 seconds to pass all the 12 cars, okay? And what about the propagation time? So you can think about this is a transmission delay, right? And what about the time to propagate the car from the first booth to the final booth? So it's about 100 kilometers divided by 100 kilometer per hour, right? It's about 1 hour. So how long do we need to take? It will be totally 1 hour and 120 seconds. So totally it would be 26 minutes. Okay, so this is a case that we have a long distance, but comparably the process time is relatively smaller than the propagation time, right? So this is the first case. What about the second case? The second case is that if we assume the propagation time or propagation speed is very high, right? So we increase the propagation speed by 10 times. So that means the car, after they finish the service at the first booth, they will propagate in the line very quickly, okay? So suppose we still have the same number of the cars, and each car only takes about 1 minute to service, okay? And how long will the whole caravan will pass from the first to the second one? Okay, so we can think about that after the first car finishes the service, it will spend 0.1 hour to finish the distance between the two booths, right? So 0.1 hour is about 6 minutes. And itself will spend 1 minute to do the service. So totally after 7 minutes, the first car will arrive at the second booth. Am I right? And after 7 minutes, so you can think about each car will spend 1 minute, and there is still, because we have 10 cars, right? There are still 3 cars still at the first booth. So here's a summary. So if we use this example or based on this assumption, that means after the first car arrives the destination or arrive at the second booth, there are still 2 cars or 3 cars in the queue. Okay, so this is different from the first one, because first one the 2 booths has 100 kilometer, but the speed for propagation is only about 100 kilometer per hour. Now we have a 10 times faster propagation speed. So that means the car, after the first packet arrive at the destination, there's still something in the queue. Am I right? So if we are, so let me ask a question. So if there is a car added to the caravan, right, after added to the line, every minute, how many cars would be in the queue for the following time? So if I assume that in the following time that every minute there will be 1 car arriving, a new car arriving. So how many cars would be in the queue for the following time? Anyone know that? Or is there any question in the chat? Sorry, I didn't check. After how long? I mean, okay, so let me clarify the question. So the question is that, so you can see that every minute, the first booth will take care of 1 car, right? And I assume that there would be another car added into the queue every minute. Okay, so for example, in the next 5 minutes, right? So how many cars would be in the queue? Every minute there would be 1 car out, but every minute that would be 1 car in, right? So the queue would be in a balance status, right? So, and considering, okay, Chris, you are saying that there will be 10 cars in the queue. Okay, I mean, sorry, maybe I also have a confusion for you. So I mean, so here starting from the after 7 minutes, okay, after 7 minutes, there will be only 3 cars in the queue, right? And after the 7 minutes, and we add each car into the queue. Okay, so that means, yeah, but I think your answer is still right, but based on the different assumption. But based on my assumption, after the 7 minutes, we add 1 car into the queue, and then the queue would have 3 cars, right? But from the beginning, every minute we add a car into the queue, then that would be 10 cars in the queue. So I think your answer is still right, but my assumption is that after 7 minutes, right, we add 1 car into the queue. Okay, but anyway, my point here is that if the arriving rate is similar or very close to the processing or transmission bandwidth, right? Because every time you process 1 car, but every 1 minute you have another car join the queue, right? The queue would be in a balanced status. And then you can think about that the queue will not increase or will not decrease anymore if the queue in a balanced status, right? So that's a good thing, but you will have some queue delay. So here the queue delay is that you need to, if there were 3 cars in the queue delay would be 3 minutes. But if there would be 10 cars in the queue, the delay would be 10 minutes, right? Plus the transmission time 1 minute, plus the 6 minutes for the propagation time. So totally you can calculate how many minutes, right? In the queue, in the transmission, and in the propagation, right? So I think this is some example. If you think about the car, that will give you some idea that the first example and second example are different because the transmission time is different, the propagation time is different, or speed is different, right? Hopefully I explain this problem clearly, but in a summary that if your packet arrival rate times the packet length divided by the link bandwidth, if it's close to 0, that means the queue delay is very small, right? But if the L times A divided by R is close to R, that means the queue is almost in a full status. But I mean, at least in a balanced status, right? So it's not a decrease or it's not a increase. It's in a balanced status. But because the queue originally has some packets, so the queue time would be also high, right? But if L times A divided by R is larger than 1, so if you think about the previous case, every minute you will arrive more than 1 car. You arrive 2 cars or 3 cars. Then you can think about the queue would be ever increasing, right? From 10 cars to 11 to 12 and for infinite. But the line, if they have some capacity, right, they cannot get any car to the service, right? So if you think about the highway, right? If L times R, A divided by R is close to 0, that means almost there is no car in the queue and the highway will be almost empty, almost free, right? And the delay would be very small. But you can think about during the traffic time in Seattle or in Spokane, right? So the queue delay would be very large. Okay, and if you are arriving more cars and the queue increasing and maybe the service cannot be finished, right? And the packet will be lost eventually. Okay. So let me check one. Okay, I think that's close to the end of the class, and this is the final slides about the delay and the routes, right? So there is some program can give you some idea about the delay between the source to the destination, right? We can use some program to measure what is the internet delay from your, for example, your endpoint from your IP to the other service or other IP address, right? We can show you a quick demo about how to measure the delays, but I tell you that there is some program can give you some idea, information about what is a delay. Okay, so I think that's it for today. Next lecture we will talk about the packet loss and some other stuff. Okay, so is there any question before you leave? Yeah, I think S, thank you for your comments. I think you have many detailed comments for the other students. I really appreciate that. Yes, I think your comments are correct, right? The transmission delays, the definition of transmission delay, propagation delay, and I really appreciate that. So sometimes if I don't cover some details, yeah, so you can, or some of your, if you want, you can also put more details here, and it's very welcome to have a discussion here. Okay, thank you, S.
Oh, yeah, thank you. I actually am just copying some of the that you're covering. If I see stuff in the book, I'm just putting them in the chat.
Yes, thank you so
Yeah,
much.
yeah, cool.
It's very helpful. Yeah, for other students, if I don't cover that, other student may look your text. Yeah, I appreciate it. Thank you.
All right, thank you. Have a good day.
Okay, have a good day. So if you don't have any question, let's see on Wednesday. Okay, so I will upload. Okay, oh, by the way, I will upload every day's a video to the Blackboard.
Get your mic.
So you can just look at the video if you want to check something back. Okay. Okay, thank you everyone. See you on Wednesday. Bye bye.